In this lesson, we're moving beyond drawing Lewis structures and into understanding the three-dimensional shape of molecules. Just because we draw a molecule flat on paper doesn't mean it's actually flat in real life. Molecules naturally adopt shapes that minimize the electron-electron repulsion and therefore lower their overall energy. By the end of this lesson, you'll be able to predict these shapes using VSEPR theory and AXₙEₘ notation. So there is a general approach to drawing Lewis structures that goes beyond just finding the simple Lewis structures. I call them the keep 'em happy. It was developed by a professor at University of North Carolina, Chapel Hill. I don't know what he called it, but I did get this from someone. I didn't just make it up. So in the first step, just like with the simple Lewis structures, we're going to add up the number of valence electrons that are present in the molecule. So make sure that we have the right number in our structure. And then we're going to draw a stick skeleton of the molecule. That's where you're going to take the central atom and just stick all the other atoms to it. Don't daisy chain your atoms together. You want to satisfy the octet rule for all of the atoms in the molecule. The octet rule means that in general things want to have at least 8 electrons around them. The terminal atoms will have 8 electrons around them as long as they aren't exceptions, and the central atom will have at least 8 electrons around it. The exceptions are hydrogen only needs 2, and that's because it's a first period element. It's really small, that's all it needs. And boron only needs 6. What happens is its pz orbital gets distorted and kind of gets out of the way, so that it doesn't need that extra pair of electrons. All right, so then once you have your structure and you've got all of the extra lone pairs added to it, you want to compare what your structure has to what you are supposed to have. If there aren't enough electrons, the molecule is unhappy, but notice that's in quotes, it's not really happy or unhappy. You want to add the missing electrons to the central atom. All of your corrections go to the central atom, not to the terminal atoms. If there are too many electrons, the molecule is too happy. So again, we're going to make our corrections at the central atom, and then we're going to take a lone pair on one of the terminal atoms and turn it into a bond instead of a lone pair in order to satisfy the octet on the central atom. Let's look at some examples. All right, so SF4. First thing you got to do is add up the number of valence electrons. Let me get my pen out. So we got sulfur is 6. I'll write it up here. 4 times 7 is 28. So that means we're supposed to have 34 valence electrons. Sulfur is the one we had the least number of. Also, fluorine can never be a central atom. And we're going to make our stick structure. So attach the 4 fluorines. All right, so now come on, laser pointer. The sulfur has 2, 4, 6, 8 electrons around it. Its octet is already satisfied. So we just need to finish satisfying the octets around the fluorines so that they also have 8. Right now they only have 2. Remember, each stick is 2 electrons. So we're going to go ahead and do that. Add all those lone pairs. And now we got to count them up. So we have each fluorine has 8 around it now. 8 times 4 is 32. So this molecule is missing 2 of its electrons. It has to have 34. You can't just get rid of the electrons because it's inconvenient. So this is an example of a molecule that has an expanded octet. We're going to add those missing electrons to the central atom. Now we have the right number of electrons. A lot of people get really upset about this, and they say, but no, it's got more than 8. So we got 2, 4, 6, 8, 10 electrons around it in total. Remember I said for the central atom, you want to have at least 8. And another way to look at it is that half of each bond, come on, trying to get the pen, half of each bond came from the sulfur. So if you kind of draw a little electron on there, and now count how many electrons from the sulfur are around the sulfur. We got 1, 2, 1, 2, 3, 4, 5, 6. So sulfur still has 6 electrons around it. So, and actually this is one way to tell if you have a stable Lewis structure. So this would be the optimal structure for SF4. The other thing to know about this is that fluorine, because of its reactivity and its size and its energy level, everything else like that, the only thing fluorine can ever do is form a single bond. I've seen chemistry teachers make double bonds to fluorine, and it's like nails on a chalkboard for me. So fluorine, single bond, that's all it ever does. It is a crime against nature to make double bonds to fluorine. All right, rant over. Let's go on to another example. So SO2. So first step, we have to, nope, still got laser pointer. Have to add up the electrons. So we got 6 from the sulfur plus 12 from the 2 oxygens. That means we have a total of 18. So we're going to put sulfur in the middle, attach the oxygens, satisfy the octet. So we're going to make sure everybody has 8 electrons around them. So now we're going to count. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This molecule has too many electrons. You're only allowed to have 18. You can't create electrons out of nowhere. So what I'm going to do is make my corrections at this central atom. So I'm going to get rid of this pair. It's just the way I set up the animation. So now we have the right number of valence electrons, but sulfur's octet is not satisfied. It only has 2, 4, 6 electrons around it. The central atom has to have at least 8. So what we're going to do is we're going to change one of these lone pairs into a bonding pair. And in this animation, I picked this particular pair. So we go over and we do that. And now we have the right number of electrons. I've had students in the past ask me, especially after I started talking about how nature likes symmetry, that say, well, is that the best structure? And actually, it's not. A better structure would be, come down here, we got sulfur in the middle, we got our lone pair on top, would be if you had 2 double bonds. The reason why this is a slightly better structure is because, again, like with the SF4, we have, no, wrong one. There we go. Sulfur has 1, 2, 3, 4, 5, 6 electrons around it, same as its valence electrons. This structure up here, the sulfur only has 1, 2, 3, 4, 5 electrons around it. So that makes it a little bit less stable than this alternative structure. And like I said, I had a student ask me about this once. It turns out that SO2 spends 80% of its time, and they use spectroscopy to determine this, with the 2 double bonds, and the remaining part of its time with 1 double bond. So it does make the less stable structure. It just spends more time in the double bonded one. Okay, so molecular geometry is the shape of the molecule. And remember, we saw back in the first unit that the shape of molecules affects their physical properties, like odor. We've already seen this picture. Another thing that the shape of the molecule will affect is its polarity, which has a huge impact on its reactivity, its solubility in different substances, things that it'll combine with, a whole bunch of different physical properties. So being able to figure out what the shape of the molecule is key. All right, so as I said in the introductory slide, the molecules are going to adopt whatever shape they can in order to minimize the repulsion between electrons and adjacent bonds. So the thing is when we're drawing these Lewis structures, we're putting them down on flat paper. And because the human eye likes symmetry, we tend to make them look kind of like this for like CH4. The problem is if you start thinking about it in terms of like a ball and stick model, now you don't have a balance between the repulsion between the electrons. The electrons in the bonds here and over here are only 90 degrees apart. Whereas if the atoms are on opposite sides of the carbon, so going from here, whoops, I shouldn't have clicked, all the way over to there, then it is going to be 180 degrees apart. So what they do is the molecules will twist around and go three-dimensional, so they're not flat anymore, in order to get it so that the angles between those electron pairs in the bonds is the same all the way around. So that's its balancing point. So when you have CH4, it doesn't have a mixture of 90-degree angles and 180-degree angles. All of the bond angles are 109.5 degrees. All right, so the model that we use in order to kind of put all this into words is called the valence shell electron pair repulsion theory, or VSEPR. And it just says that we're going to minimize the amount of repulsion between different the electrons in the bonds and the electrons in the lone pairs. Something that I probably should have included on this slide is that lone pair electrons take up more space. Than bonding electrons. Remember, with the bond, the electrons are localized between those two nuclei, whereas with the lone pairs, they only have one anchor point. So yeah, they take up a lot more space. And this actually has an impact on the bonding angle. And we'll see some examples of that in just a minute. All right, so there are 5 main shapes, and we have some drawings of them. So looking at the drawings, the knot in the middle of the balloons is what these are supposed to be, is the central atom. The balloons represent the space taken up by the electrons in the bonds or the lone pairs. So if we have maximum amount of bonding going on, the knot is the central atom, and the belly buttons on the balloons would be the terminal atoms. So if you only have 2 pairs of bonding electrons, and that's it, you're going to have a linear molecule. If you have 3 pairs of bonding electrons around the central atom, it's trigonal planar. It makes a flat triangle shape. And the bond angles are all 120 degrees. Tetrahedral is like the one we just saw on the previous slide, which is like CH4. And that's where you have the central atom where the knot is. And then we have the bonding pairs. And then the belly buttons are all the other atoms. For the expanded octet or hypervalent molecules, you can have 5 things attached all together to that central atom. And so this looks like we have the trigonal planar arrangement. You can kind of see the third one in the back there. And then you have one up and one down. And it's called a trigonal bipyramidal. So a triangular pyramid on top and a triangular pyramid on the bottom. And then it's got 2 different bond angles depending on whether you're talking about the ones going around the middle, that's 120 degrees, or the ones that are lined up with the z-axis, that would be 180 degrees. And then we have octahedral, which is where you have 6 things attached to that central atom. And I've had students say, well, if you have 6 things, why is it octa? Because that means 8. You have hedral means faces, so it actually has 8 faces on it and 6 vertices. All right, so this is just a screenshot of the chart that we use in order to determine what the different shape is, and I'll explain how to get this AXₙEₘ notation. So for triangular planar, that was the one where you had 3 things attached. We have the bond angle of 120 degrees. If you get rid of one of those bonding pairs and turn it into a lone pair, like in this case where we have the nitrite anion. Now the bond angle is 118 degrees, and it's just talking about the angle between the two oxygens. And a general rule of thumb is that each lone pair, I'm going to write it down here, each lone pair reduces bond angle by 2 degrees. I don't spend a whole lot of time talking about bond angles, but I thought I would just kind of share that with you. So this chart, what it is, it has the basic form, and then it has the derivatives. So for example, the trigonal planar one is like BF3 as an example. And if you get rid of one of the bonding pairs and turn it into a lone pair, now you have a bent molecule. These shapes refer to what the atoms are doing. It doesn't include what the lone pairs, as far as, we'll get there. Anyway, tetrahedral, this is like the CH4 molecule that we looked at. See, we have the 109.5 degree bond angle. So if you get rid of one bonding pair and turn it into a lone pair, notice the bond angle is now 107. There's that 2 degrees. If you get rid of 2 bonding pairs and now you have 2 lone pairs, now we have dropped the bond angle down to another 2 degrees, so 105 degrees. Actually in water it's 104.8, but that's nitpicky. All right, so steps to determining the molecular geometry. First step, draw a Lewis structure. So for pH 3, the correct Lewis structure would be like this. So 3 hydrogens attached to the phosphorus with 1 lone pair. Now you want to determine the AXₙ notation. So A and it's also called VSEPR notation. I just call it AXₙ notation because we use the AXₙ chart in order to determine it. So we have A is the central atom. And there's always only going to be one central atom. If you have 2 of them bonded together in the middle, you're going to do one at a time. And then X's are the other atoms. That's an X. And then each pair of electrons on the central atom is an E. So this one ends up being AX3E. We look at the chart, it's going to be over on the right-hand side, and we see that it is a trigonal pyramid. And then H2S, this is the correct Lewis structure. So we say, all right, well, we got, I'm not going to write it this time. So we have AX2E2. We look at the chart and say, oh, okay, well, that one's bent. All right, so let's look at a few examples. I just like this picture, that's why we have that on there. So we got this first one. So we say, well, BCl3. So we go AX3. Look at the chart, that's trigonal planar. Next one is SO2. So we got AX2E. Notice it doesn't matter whether you have the 2 double bonds or one single or one double. You're going to end up with the same shape. So AX2E, we look it up on a chart, and that's bent. Then we do this one. I'm going to pause for just a second, let you think about what it is, and say, all right, well, that's an AX3E, and that is a trigonal pyramid. And then this last one, I was trying to be tricky. Trying to get people to say that it was in X4 or E4. Remember, if they're shared between 2 symbols, that means they're bonded to them. So those are bonding pairs. So this is AX2E2. We look it up on the AXₙ chart, and that is bent. And it's the bent structure of water is why it has some of the really weird properties that it does. All right, so the assignment that goes with this one is called honing the AXₙ. There's a whole bunch of different parts to this. This last part, hybridization, I'll give you the answer, but I don't actually talk about hybridization until the next lesson. And that's because if I throw too many things at you at once, it's going to be overwhelming and nothing's going to stick. So first step, you got to add up the valence electrons. Can't get away from that. So we have 4 from the carbon, 18 from the 3 oxygens. Now if you have a charge on it like this, say, well, electrons are backwards. So if it says -2, that means I'm adding 2. So we're supposed to have 24 valence electrons. So we put the carbon in the middle, attach the oxygens. So carbon is in the second period, and so it cannot have an expanded octet. It doesn't get dots in general, so I'm going to say, just give a general rule, carbon has 4 bonds. There are some cases where it has 3, but again, we're trying to simplify things as much as possible, and no dots. So it's like, all right, carbon has 4 bonds, no dots, so I'm going to make a double bond to one of the oxygens. Now I'm going to satisfy the octet for the oxygens. Carbon has 2, 4, 6, 8. It's already done. So we add these electrons. That's terrible. And then we got oxygen, so only got the 2, the doubly bonded one. So now each oxygen has 8 electrons around it. I don't like that. It looked like I was drawing a circle. So 8 times 3 is 24, so we have the right number of valence electrons. So that is the correct Lewis structure. Now we want to do the AXₙ notation. So we have AX3, and we look that up, and it is, and I'm going to use some abbreviations. So the geometry is trigonal planar. And then the hybridization actually comes from the subscripts on the X's and the E's. So the hybridization, the superscripts have to add up to be the same thing. Like I said, next lesson we'll see why. So this one would be S1, P2. And that would be that one. Got another example. So we got C2H2. So we got the 2 carbons are going to be in, we got to add them up first. So we got 8 from the 2 carbons, plus 2 more from the 2 hydrogens, so 10. So we put the 2 carbons in the middle. Attach the 2 hydrogens. When in doubt, make it symmetric, because that gives you the most stability most of the time. So hydrogen, as soon as you make a bond to it, it's done. It's one of the exceptions. Carbon needs to have 4 bonds. We got 1, 2 on that carbon. So 3, 4. 1, 2, 3, 4. So both carbons have 4 bonds to them. And now we have to check our valence electron count. So we got, trying to turn my laser pointer around, 2, 4, 6, 8, 10. So that means that that is the correct structure. Now we're going to do the AXₙ notation. So this is the point where students get confused. They say, but I have 2 central atoms. How do I know which one is which? It doesn't matter. That's why this symmetry is looking for the most symmetric structure is good. Because if you pick this one, we got AX2. And then if you pick, let me change colors. Change colors. There we go. The other one, it's still AX2. The atoms don't know what the chemical identity of the other atom that is bonded to it. They just the geometry just cares if there's an atom or a lone pair bonded to it. So that means our AXₙ notation is AX2. And if you look up at the top of the AXₙ chart, that I showed you earlier that tells you it is linear. And then the hybridization for this one would be S1P1, or SP, once you get into organic chemistry. They don't use the ones. All right, finally, to then wrap up. VSEPR theory says that we are going to minimize the amount of repulsion between electrons in bonds and in lone pairs. Just remember that the amount of space that the lone pairs take up is a little bit bigger than the bonding pairs. So we have the 5 basic electron geometries, molecular geometries: linear, trigonal, planar, tetrahedral, trigonal bipyramidal, and octahedral. And then all the other ones are derivatives of those basic 5. Like I said, lone pairs repel more strongly. There's a 2-degree decrease for each lone pair you have on that central atom. We want to use AXₙEₘ notation or VSEPR notation in order to predict geometry. And then always make sure you draw the Lewis structure first. Check your valence electron count before you start trying to determine the AXₙEₘ notation. So that's it for molecular geometry. Next time we're going to be looking at hybridization and why this matters. So thanks for listening.